All right, so we're ready to do section 8.2, which is titled Hypothesis Testing in 4 Steps. So the book recommends 4 steps to do hypothesis testing, and this hypothesis testing does vary a little bit by textbook, so we're going to follow what our textbook does to do this. But the overall process is the same, but some small details do vary between statisticians, right? Um, so the big thing in this section that we want to be able to do is conduct a hypothesis test involving a population proportion, right? So this next slide talks about the 4 steps in hypothesis testing that that we're going to do. So the first step is to hypothesize. So we want to state our hypothesis about the population parameter, right? So remember, hypothesis testing always has to do with the population parameter, right? We're never making a claim about a statistic, right? About a sample. So the hypothesis testing, right? We have two hypotheses, right? We have a null hypothesis, right? Which is denoted by HO. And one thing you want to remember is the null hypothesis is always has an equal sign, right? So for example, we could have our population parameter equal to P naught, right? And this P naught, the text uses that notation for the population parameter that we claim is true from the null hypothesis, right? So that will be provided to us. And then we also have a alternate hypothesis, right, which we can denote by HA, or I mentioned before, some texts will use H sub 1, right, for the alternative hypothesis, right? So we have the null hypothesis, which always has an equal sign, and then we have an alternate hypothesis. And the alternate hypothesis can come in 3 different ways. So we could have P being less than P naught, P sub 0. We could also have a null hypothesis of P equals P naught, right? So that's still going to be the same, but I could have an alternate hypothesis of P greater than P naught, and then I could also have another scenario where my null hypothesis is P equals P naught still, right? But my alternate hypothesis is P does not equal P naught, right? So in other words, P is different than P naught. So we have these 3 cases. So this this scenario, right? This guy, when P is less than P naught, we call this a left-sided test. Left-sided, right? When if our alternate hypothesis is claiming that P is greater than P naught, this is what we call a right-sided test. Right-sided. And so left-sided hypothesis test, a right-sided hypothesis test, and then H sub 0, if we have an alternate hypothesis of P not equal to P naught, right? In other words, it's different. So it could be either less than or greater than. We refer to this as two-sided, right? So another thing I just want to remind us of is painting a picture, right? So we're going to be given some alpha value, right? Typical, this could be 0.05, right? Right, and so we talked about alpha last time, right? Right, so, and also if you remember, alpha represents the probability of rejecting the null value when it's true, right? So in this alpha value will be provided to you, right? So 0.05 is the most common, but we could use like 0.01, 0.001. Those are also common ones to use, just depending on your data and in which value that you want to be given, right? So what we end up doing is if we get a p-value that's less than 0.05, in other words, less than alpha, then what we do is we reject the null hypothesis and we accept the alternate hypothesis, right? We say there's statistical evidence to suggest that this guy is true, right? If p is bigger than alpha, then we stick with this the null hypothesis, right? We stick with that being true, right? So the general idea, the p-value is the area under the curve, right? So if we have a left-sided value, then we're going to use the z distribution, right? So the z distribution is a normal distribution. We're going to calculate a z value, right? And find this here, right? So here's our z calculated, right? We're going to calculate this. With the left-sided test, we're going to find the area to the left of this, right? The left tail area. Where with a right-sided test, we're going to find some z calculated, right? And we'll assume that it's in the same place. Then we're going to find the area to the right, right? And then with a two-sided test, it turns out that since we have a normal distribution, it's symmetric, right? So we'll end up finding the area to the left and to the right, right? So we're going to have some z calculated here. And there's also going to be its counterpart over here that's going to have the same area here and here, right? So both of these areas are the same. Right, so if that left side is equal to p, this will also be equal to p. Right, so when we do a two-sided test, if we find one area, we can just double it. Right, so if I know the left-sided area, then I just double that. Right. So that's what we're going to be doing. Right, and remember we've already worked with finding area under a curve already, right, with a normal distribution. So that part shouldn't be brand new to us. Right? So that's with the hypothesis, right? So preparing, we're going to state a significance level, right? So we're going to pick an alpha, right? Choose an appropriate test statistic, right? So we're going to calculate z calculated, right? And remember, z is equal to p hat minus p naught divided by my standard error, right? Where my standard error is equal to p naught times 1 minus p naught all over n, and take the square root of that, right? So these are two formulas we went over last section, right? So we take our observed value minus our null value and divide by the standard error, right? That's the general item, right? And then we also want to check some conditions, right, to make sure that this makes sense, right? Because if we don't believe that we have a normal distribution, then it doesn't make sense to proceed further, right? So we need to check those conditions in the book, and they're on the next slide, right? So then we're going to use some technology then to find my observed value, right? So this find my observed value of the test statistic. So my C calculated, the book is calling this observed. That's fine too, right? So we can think of this as my Z value. That's observed, right? So find this value, and then we're going to compare it to the null hypothesis and say what we get, right? Find the p-value to measure my level of surprise, right? How surprised are we that this value could be true, right? And then we're going to either reject or not reject the null hypothesis, right? And we never fully accept, right? We say, you know, based on statistical evidence, this appears to be true, right? Type of thing, right? What does this mean in context? So we need to interpret that a little bit, right? So here are my conditions to check, right? Don't forget. So we want to make sure we have a random sample, right? Also, I want to make sure I have a large enough sample size. So to check that, I want to make sure that I have at least 10 expected successes and at least 10 expected failures, right? So we check that with these two formulas, right? Also, we want to make sure we have a large population, so we want at least 10 times bigger than our sample size, and that is if we have without replacement, right? And then also we want to make sure we have independence, so we want to make sure that each observation has no influence on any others, right? So an example of dependence is, let's say I had student 1, student 2, student 3, so forth, right? Maybe I collected data on 3 students, which we would have more students than that, but I'll just do 3 for this simple example. Let's say I have maybe they have 3 exams in the class, right? Exam 1, exam 2, exam 3, right? So let's assume that I give the same exam 3 different times, right? At 3 different points. So these would be dependent on each other, right? This would be a dependent test because I have exam points over the same student, right? So all these scores would not be independent of each other, right? So that's just a classic example. Like if we give the same test at different times on each student, that's an example where we have a dependent. We have dependence, not independent. All right, so the next slide, we start with an example looking at the death penalty. So we're told that in 2009, it was estimated that 63% of Americans supported the death penalty. In 2014, a Rasmussen poll found that in a random sample of 943 Americans, 538 supported the death penalty. Do we have evidence that supports of the death penalty has declined among Americans since 2009? Right. So we're trying to see if the support of the death penalty has declined. So here's walking through the example. So the first thing that we want to do is have hypothesize, right? So the null hypothesis is we're checking has the support not changed since 2009, right? In other words, p equals 0.63, right? The alternate hypothesis here is trying to see has the support declined. So decline referring to less than, right? So we have a left tail test here. And then the next thing we want to do is make sure that all of my conditions are met. So the sample is random and independent, right? We can there's nothing that, so we're told that it's a random sample, and there's nothing to suggest that we fail any independence here, right? Nothing to believe that. Next, we check the sample size. So I can expect at least 10 successes and at least 10 failures, right, by using these formulas, so we're good. And then we check the population, right? So it's definitely, we can definitely support that the population of Americans is bigger than 10 times 943, right? So we had 943 in our sample. So then next we're able to make some computations, right? So next we want to calculate p hat, right? So we had 538 divided by 943, and we get 0.5705. And then calculate the standard error, right? So the 0.63 is the p naught, right? That we had earlier. So in doing so, we get this 0.0157 standard error. So then now we need to calculate the test statistic. So I plug these values in, the p hat minus p sub 0 divided by a standard error, and we get a z-score of negative 3.82, right? So kind of the picture that we have right now is here's my z distribution, right? Here's a z-score of 0, here's a z-score of negative 3.82, and I want to find the area to the left, right? So I want to find this area, right, which we're letting be my p-value. If p is less than alpha, then we're going to reject the null hypothesis, right? And we accept the alternate. If p is bigger than alpha, then we fail to reject, right? Or we don't reject, right? So that's what we're looking at. So we know it's very unusual to be 3.82 standard errors below the mean, right? But in practice, we're going to use technology to compute the test statistic and the p-value, right? So we know it's unusual, but we want to make sure get it with a value, a number, to make sure how unusual. So we can find that probability, that p-value. So here is just a screenshot using StatCrunch, right, which comes with my StatLab, which you can use that in your homework if you'd like. But I would so this walks you through, right, getting those p-values. So we end up getting a p-value very, very low, right, 0.00006673, right? So here it walks you through how to find that with the StatCrunch, right? But again, we're not going to use StatCrunch. We want to use the TI calculator, right? And I can also show you how to find that using R, right? So to do this in the calculator, let me open up my calculator. We're going to go to stat, which is here, and then go over to test, and we want to do the 1 proportion z test, right? 1 proportion z test, option 5, right? So I need to enter in p sub 0, right? So p sub 0 is, so if we come up here, p sub 0 was 0.63, right? So we put in 0.63. Next, I'm going to put in my x value, right? So my x value was 538. And then my n value was 943, right? So plug those in. And then I need to come down here and pick what kind of test I have. So we had p is less than p naught, right? In my alternate hypothesis, right? So then we can go down to calculate and get the p-value. Oops. Right, so my p-value here is 7.7 e to the negative fifth, right? So that's in scientific notation, right? That's going to be really, really small, right? Which is similar to what we got above here, right? So it looks like did some rounding, right? So here we only plugged in the z value of negative 3.82, right? But in this case, using this test in my calculator, I used a more accurate z-score, right? So we didn't round the z-score at all. All right. So you might wonder what the draw feature does. Right, so if you have the 1 proportion z test open up in your calculator, right, and instead of going down to calculate, if you go down to draw, right, what it does is it will draw the z curve, right, and tell you what your z-score is and what your p-value is, right? So another way to do that, right? So it's really a small value, right? So notice here this p-value, it says less than 0.0001, right? So when we report p-values, when you're doing research, if you have a p-value bigger than 0.05, typically you just report it, right? So let's say so if you had, like, I don't know, p equals 0.23, right? Then you would just say p equals 0.23. If you end up having a p-value that's in between 0.05 and 0.01, then we would say that p is less than 0.05, right? It's typical to say that. We just say it's less than 0.05. If we have a p-value that is in between 0.01 and 0.001, right, then typically we would just say that p is less than 0.01. And then lastly, if p is less than 0.001, then we just say that p less than 0.001, right? So these are common ways to say p-values in research, right? So notice here this p-value is just listed as less than 0.0001. That fits into this category, right? So telling us that that's very small, right? All right. So that's what this was doing here, right? 1 e to the negative fourth is point, and then 3 0 is 1, right? So that's the draw is reporting that in that form also, right? So you might see that from time to time. All right, so now more about p-values. So remember that the calculation of the p-value depends on the sign in the alternate hypothesis, right? So if we end up having, if alternate hypothesis contains does not equal, then it's a two-sided test, right, as I was saying before. So then the p-value would actually be the total of two shaded regions, right? So we call this a two-sided p-value. So to find this p-value, I would need to find this area and add it to this area, right? But since it's symmetric, I could also just take 2 times one of the areas, right? One area to get the p-value, right? So I could find 1 multiplied by 2, or if you found both, it would be the same, right? Because it's symmetric. So more about the p-value. If we get a less than or a greater than, then we have a one-tailed test, right? As stated before. So if we have a less than, we have a left-sided test. So the p-value would be here, this area, right? Then on the next slide, just another graphic on a right-sided test, right? So if p is bigger than p naught, I want to find this value. So this is my p-value, right? So it's important to be able to draw the curve when we're doing this and think through what area we're trying to find, right? So here's another example. So it says, suppose a poll of 250 randomly selected voters in a city found that 140 of them favored increased funding for public libraries. Based on this poll, could we conclude that a majority of voters in this city, more than 50%, favor increased funding for public libraries? Use a significance level of 0.01, right? So here, this is telling me alpha is 0.01, right? That significance level. So if we have a poll of 250 randomly, so that's my n value, right, is 250. So p naught, right, is equal to x over n. Excuse me, I said p naught, but I mean p hat, right? So we found 140 of them favored increased funding for public libraries, right? So p hat would be equal to 140 out of 250. So 140 out of 250 is what? So 140 divided by 250, 0.56. Right? And then we're looking at, based on this poll, could we conclude that a majority of the voters, more than 50%, favor increased funding? So we want p naught to be 50%, 0.5. Right? That's what we're testing in our null hypothesis, right? And we know alpha is 0.01. So we identified all of those things from here, right? So if we go to the next slide, we can set up my hypothesis testing, right? So remember, for our null hypothesis, always p equals p naught, right? And I found p naught to be 0.5. And then we're trying to see, if you notice, it says, can we conclude that the majority of voters, so it says more than 50%, right? That's what majority means, more than 50%. So more than means we need to use a greater than symbol here, right? So that's where that greater than symbol came from. So now we need to prepare. So we need to check the sample size. Is it big enough? So if I take n times p naught, right? So we had 250 in our respondent. P naught is 0.5. We get 125. So we would expect 125 successes, and we would expect 125 failures. So since both of these are the same number and they're bigger than 10, that means my sample size is big enough, right? So remember, we want at least 10 successes and 10 failures to be expected. Next, check the large population. So we need to assume that there's more than 2,500 voters in the city, and that seems like a fair assumption, right? So a city we could assume has 2,500 voters. So that's good, right? So we checked all of those assumptions. Next, we need the z statistic, right? So z is equal to, right? So we had p hat minus p naught all divided by the standard error, right? And the standard error is equal to the square root of p naught times 1 minus p naught all over n, right? So if we plug our values in, we can find this z statistic, right? So here StatCrunch is giving us a z statistic, and there's my p-value, right? So they're saying we have a test statistic of 1.9, right? So if I find this by hand, right, so p hat we found above to be 0.56, right? So I would have 0.56 minus p naught, which is 0.5, all divided by the standard error. So I need to calculate standard error. So my standard error would be equal to the square root of 0.5 times 0.5, right? 1 minus p naught would be 0.05, or 0.5 still, divided by n. So we had, what, 250, I believe? Yeah, 250 in my sample, right? So if I take the square root of 0.5 squared divided by 250, right? I get a standard error of approximately 0.03, we'll say. 0.3, we'll go ahead and do 1/6, right? Try to be more accurate, right? The more decimal places we do, the more accurate that will be, right? So 0.0316. So then if I take 0.56 minus 0.5, right, and then divide that by 0.0316, we get 1.8987, right, for my z statistic. So to paint a picture, what's going on is, let me go to the right a little bit, right? So to paint a picture, here's a z-score of 0. Here would be, somewhere over here would be a z-score of 1.8987, right? And what I'm trying to find is the right tail test, because we're testing if p is greater than 0.5, right? So I'm testing this, finding this area. I need to find this. This is my p-value. So our StatCrunch is showing this. This is 0.0289, right? 0.0289. So another way that we can get this is you can go to statistics, go over to test, right? And we want option 5, the one proportion z test still, right? So p naught was 0.5, right? 0.5. My x was, let me go back up here. X was 140. N was 250. And we're testing if it's greater than p naught, right? So I can go down to calculate and find that, right? So there's my z value given to me, right, that we calculated. And there's the same p-value, right, of 0.029. So you can find that in the calculator just as easily, right? So now we need to make a conclusion, right? So remember, my significance level was 0.01 that was given to us. So P is equal to 0.0289, which is bigger than alpha of 0.01. So we fail to reject. So we do not reject, or we fail to reject the null hypothesis, right? So we say that we cannot conclude that the majority of voters support increased public library funding, right? That's an interpretation of that, right? That's a conclusion. So you should always state the conclusion in the context of the problem, right? So that way you understand what we did and what everything means, right? All right. So now I want to walk through. So let's see. So we did an example of a left tail and a right tail test, right? I believe, right? So above here, yeah, we did a left tail test, right, with the death penalty. And then I did an example of a right tail test with the increased library funding. So I put two examples here. That we can walk through, right? So this one is less than, so this would be a left tail test, right? This one here we're testing, is it different? So this would be an example of a two tail test, right? So let's walk through that, right? So step by step. And if you go in your book to page, let's see, I think it's like 396. No, that's not it. All right. So if you're unsure of the steps to do with the hypothesis testing, right, on page 364, it walks you through the steps to do and the conditions, right? So step one that the book is suggesting is to state our hypotheses, right? So step one, we want to say the alternate and the null hypothesis and the alternate hypothesis, right? So I might even go through and identify all the things here also, right? In the example. So we have a random sample of 27 records, right? So 27 would be equal to n, right? That's my sample size. X is equal to 15, right? Those are the number of successes, right? 15 intoxicated drivers in an accident, right? So p hat is going to be equal to x over n, which is 15 over 27, right? So this is going to give me, so let me get out of this. So 15 divided by 27. We'll do 0.56, right? We are rounding here, right? So when I find my p-value, if I were doing this by hand, it might be a little different than using technology just because of the rounding, right? So we have p hat calculated, and then I want to find p naught, right? So what are we testing? We're testing 77%. So we're assuming that p naught is 0.77, right? 77%, right? That should be everything we got, right? And alpha, so we want alpha equals 0.01. So that was given to us. So my alternate hypothesis is that my population parameter p is equal to 0.77, right? Equal to p naught, right? My alternate hypothesis, we want to test if it's less than, so we're testing if p is less than 0.77, right? So that's step one, right? Step 2 is we want to prepare. So step 2 in the book, we want to prepare. We want to state my alpha value, which is 0.01, right? That's one thing in step 2. And then also we want to choose a test statistic, and so the test statistic that we're going to use is the z, right? So we're going to use z for proportion, for population proportions. And then also we want to make sure that all my conditions are met, right? So the conditions are, we want to make sure we have a random sample. So check conditions. So the first condition, do we have a random sample? And we do, right? It says random sample. My second condition is, do we have a large sample size, right? So to check that, we want n times p hat. We want this bigger than 10, bigger than or equal to 10, and we want n times 1 minus p naught bigger than 10, right? So checking the sample size. So n is 27, so we would take 27 times 0.77, right? And is this bigger than 10? And then we would check 27 times 0 would be what, 23. Is this bigger than or equal to 10? All right, so we can come over here and check. So 27 times 0.77. So that one's good. If we take 27 times 0.23, that is not bigger than 10, right? So this one is not bigger than 10. So this failed one of the conditions, so it wouldn't make sense to follow through with this, right? So in this case, we would be done here, right? We wouldn't want to continue because one of our conditions aren't met. So typically what you do is maybe get a bigger sample to do the test, or like if you fail a test thinking that things are not, for example, if we had to assume normality, right, you might want to investigate that further if you believe that something failed it and so forth. So since this fails, we would not want to do anything with this data, right? We would essentially need to get a larger sample size, right, to work with this further. All right, so we're done with this example. So then moving on to the next example. All right, so we can do the same steps. We're trying to, so here it's saying, let me scroll up a little bit. So are most government student leaders extroverts? So according to Myers-Briggs, estimates about 82% of college student government leaders are extroverts. Suppose that a Myers-Briggs personality preference test was given to a random sample of 73 student government leaders attending a large national leadership conference, that the 56 were found to be extroverts. Does this indicate that the population proportion of extroverts among college student government leaders is different, either way, from 82%? Use alpha equals 0.01, right? So again, big things we want to do is we want to identify each of our parts, right, from the sentence. So that's where I would start. So we had a random sample of 73 students, so n equals 73. This number, or the number of people who are extroverts, so that's x. So p hat, this is a p hat, would be equal to 56 over 73, right? X over n. So 56 divided by 73 gives me 0.77, right? So p hat is 0.77, right? So that means that 1 minus p hat would be 0.23, right? So remember 1 minus p hat, or we can call this q hat, right? So that's the point estimate for the failures, right? Q is failures. see. So 82%, that is P naught, right? That's what we're assuming to be true, what we're testing in my null hypothesis. So that's what we need to start with. Step one is identifying the null hypothesis and the alternate hypothesis, right? So the alternate hypothesis is that is my population parameter, is that equal to 0.82, right? We don't know. We're trying to see, is there evidence that suggests that? And then my alternate hypothesis is, since we're doing is different, that means that P is not equal to 0.82. Right, so this is going to be a two-tailed test, right? A two-tail hypothesis test. Right? So then we go to step 2. So step 2 is to get ready to test, right? It says state significance level alpha is 0.01, right? That's given here. Let's see, we need to choose a test statistic, so we're going to use the Z test statistic. And we need to check conditions, right, before I move any further. So condition 1, do we have a random sample? So I believe that was stated, right? Random sample, so we're good there. Right, so we check conditions. So first, do we have a random sample? Good, we do, right? Second condition is, do we have a large sample size? So we need to check my sample size. So I take is n times p naught, is that bigger or equal to 10? And then check n times, we could do q naught, right? Or 1 minus p naught. Is that bigger than or equal to 10, right? We don't know. We're testing that. So let's see. So n was what? 73. So we'd have 73 times p naught, which is 0.82, right? Is this bigger than or equal to 10? So 73 times 0.82 is 59, right? So this is bigger than or equal to 10, so we're good there. And then we need to test n, so 73 times 1 minus p naught, so times 0.18, right? Is this bigger than or equal to 10? So we do 73 times 0.18, and this is bigger than or equal to 10, right? So that's good. So we can assume we have a large enough sample size, right? That condition is met, right? Another condition is we need a large sample size, or excuse me, large population, right? We just did sample size. So we want to know is 10 times n, which would be 10 times 73, is it safe to assume that my population is 730? And I would say yes, right? We can assume that there's 730 student government leaders, right? This is in the United States, and even if we had just one, so student government leaders, I would say there's at least probably 3. So we could assume that there's at least 730, right? I think that's a fair assumption. And then 4, we check independence, and there's nothing here to suggest that one observation or measurement has any influence on one another, right? So this looks to be met, right? So we met all our conditions, so now we can start to proceed, right? So then step 3 is to compute, right? So we want to find my z value and my p value, right? So remember, z is equal to p naught minus, or excuse me, p hat minus p naught all over standard error, right? So I apologize. I don't know why I want to keep saying p naught but writing p hat when I do mean to say p hat, right? So p hat minus p naught divided by standard error is my z statistic, right? So p naught we calculated above to be 0.77, right? So 0.77. P naught, or P sub 0, was 0.82, right? 0.82. So minus 0.82. And my standard error, so standard error is equal to P naught times 1 minus P naught all over n, take the square root of all that, right? So this would be 0.82 times 0.18 all over n, 73, right? Take the square root of that, see what standard error gives. So if we take the square root of 0.82 times 0.18 divided by 73, we get a standard error of, we'll do 0.045, right? So 0.045. So we can now calculate z, so 0.77 minus 0.82, and then divide that by 0.045. We get a z-score of minus 1.11, right? So just so we can see what's going on, what you're visualizing here is we have this z distribution, right? So this is a z distribution, normal distribution. So z, remember, is normal with a mean of 0, standard deviation of 1, right? Normal distribution. So here is 0. I got a z statistic of negative 1.11, right? So this would have some area on the left. But then since we have some symmetry, if I come over here to the z value of positive 1.11, then I would get this area. And this area is equivalent to this area, right? Both areas on both sides are the same. But since we're doing a two-sided test, I need to find, my p is going to be 2 times one of the areas, right? So if I find this area, I double it to get p, right? Or if I was able to find this area, I'd double it to get p. So we can go to we just go into stat menu, right? Go over to test, and then we can go to 1 proportion z test, and we need to type this in, right? So p naught was 0.77, right? 0.77. My x was 56. N was 73. And we're doing this first one, right? Not equal to, so I can go down to calculate, and we get a p-value, right? So I'm getting a p-value of 0.95. Alright, so as soon as I got this value of p-value 0.95, you should have been screaming at me that doesn't make sense, right? Because if you remember the empirical rule, if this is -1 and if this is +1, right, we would expect how much of the data in here? 68%, right? So this p-value seems way too high, right? So this area plus this area should not be like 95%, right? If this much is 68%. It doesn't really make sense, right? So this tells me I must have entered something in incorrectly, right? And you may have noticed when I was doing that, right? So if we were doing this in class, you probably would have yelled at me, Tyler, you typed in the wrong thing, right? But since we're not, we have to go back and fix it. So if I go to the stat menu and go to test, if I go to option 5, you'll notice that I put in the incorrect p-naught value, right? This should be 0.82. Right, 0.82, right? That's what p-naught was. So 56 for x is good, 73 for n is good. All right, so that should be my error. So let's see if that corrects that. Go to calculate. Now I'm getting a much more believable p value, right? So this is saying p equals 0.2396, right? So if I take P divided by 2, that would be the area of the right tail, which P divided by 2 would also be the area of the left tail, right? So if we take 0.2396 divided by 2, then I know this area is 0.1198, and this area is 0.1198, right? So my calculator already does that for me, so I don't necessarily have to double it, right? All right, so if we were doing this in R, you know what we would type in. So let me pull up R. So let me go split screen with this too. All right, and I'll make my font large in R. So let me just show you how you could do this in R real quick to make sense of it. Right. So in R, my calculator is nice because it calculates that area for me. I just plug some things in and it finds it pretty easy, right? But using like R or using a table doesn't work out as nice, right? So with R, remember, R is always going to find the left tail, right? So we use the pnorm command, right? So pnorm, and then I need to put in my z statistic. So let me find where we calculate the z. So we got z to be negative 1.11, right? And then I'm going to do comma, and then type in the mean, which we're doing z distribution, so the mean is 0, and then the standard deviation. So the standard deviation of a z distribution is 1, right? So if I do that, I'm getting the area to the left, right? So essentially, my R is trying to estimate this value, right, to the left. But we have to consider that when we use a TI-83 or 84 graphing calculator, these z-scores and the p-hat are not rounded, right? So they're not rounded, so we don't have this rounding error, right? So like, for example, negative 1.11, that wasn't exact, right? And also we rounded the standard error to get that, right? So that's why we're a little off. So on your exams, I'll accept both answers, right? If you want to use a table, so if you use a table, you're going to get similar results like this back, right? So I can pull up how to do this in a table also, right? So to finish this off though, right, just so this makes sense, is when I plug this into R, it's telling me the area to the left always, right? So negative 1.11. So this R is saying is 0.1335, right, roughly. But we need both sides, right? I need this side too of 1.11. So this area would also be 1.335 roughly, right? So what I need to do is take 2 times p norm of negative 1.11, comma 0, comma 1. And that would give me the complete p-value, right, for the two-sided test. So remember, to do a two-sided test, we have to double, right? And if you're doing a right-sided test with a z distribution, right? So let's say this is a z-score of, I don't know, 1.3, right? Then to plug this in R, what you'd want to do is we could just come over here and do negative 1.3 and find this area, right? Because this area would be equivalent to this area. So it's always easiest to find the left area, right? Because it's the same as the right, right, with a normal distribution, because it's symmetrical. So if you use R or use a table, they always do left, right? All right, so running out of time on this video. So let me pull up real quick, pull up a table in the textbook. Right, so I'm just opening up the e-text. At the end of chapter 10 are the appendix. So appendix A are the tables, right? So if we go to the tables of, so this is the table of standard normal curve probabilities, right? That's what we want, z-scores. So first we have to figure out what my z-score was. So my z-score was what? Negative 1.11, right? So I'm going to be in this row here. And let me see. So we're going to be in this row here, right? Oh. Computer's acting really slow here. Alright, so we want here 0.01, we want to match that up with negative 1.1, right? Because remember, over here, this is the ones place in the tenth spot, and then over here is the hundredth, right? So 1.11, so we want to be in the second column, match up with 1.1, and we get this p-value, which I mark that up. Let me see if I can refresh this, get rid of that. So let me go real quick to make sure this is clear. So we were on this page. So negative 1.1, right, will be here. So I'm looking for that value. 1.11 would be here. 0.1335, right? So that's the area of the left, right, that we found in R. So if I double that, that's the p-value I need since I'm doing a two-tailed test, right? All right, so that should get you through this section okay. Thanks.